Welcome to the second week of the lecture series on fluid inclusions in minerals. In the introductory set of lectures, we got ourselves introduced to this technique of fluid inclusions. Fluid inclusions are tiny microscopic cavities sealed within the solid lattice of the host mineral. They are of different there is a wide diversity in the way they occur in the inclusions in the minerals, and they have to be studied, they have to be understood, categorized, classified, and then subjected to meticulous microthermometric and microanalytical studies to retrieve important information, which will be useful in synthesizing and addressing broader art processes like ore deposit formation, metamorphism, deformation, and many more. So, to begin with, we plan to, in this particular week, we plan to cover two important aspects of fluid inclusion studies. One is fluid inclusion petrography, and we also intend to get ourselves introduced into the principles of microthermometry that is essential to they remain as a background information, essential background information when we study them under the microscope or do microthermometric experiments. So, let us first try to understand what is actually microthermometry. What do you understand by microthermometry? So, microthermometry is essentially what we mean is that we see the inclusions under the microscope, and primarily we are interested in their thermal characteristics, that means the temperature. We are interested to know what was the temperature of the fluid that gave rise to this particular mineral, because we might ask ourselves why temperature, because of the fact that the fluid that we are interested in are essentially very diversely sourced. This fluid could come from could have come from a much deeper part of the earth's interior, maybe from the mantle, which could be a juvenile fluid, or could be a fluid which actually have been recycled into much deeper part of the mantle through the mantle metasomatism, and these type of fluids are essentially to be expected to be much high in their temperature. The fluid could have been sourced from a crystallizing felsic magma. The fluid could have come from dehydration or devolatilization of sedimentary rocks, which give them metamorphism. So, during the process of metamorphic devolatilization, and we can call them as metamorphic fluid. They could have come from shallow circulating or kind of fluid which are trapped in the sedimentary basins. They can be basinal fluids, or we call them as connate fluid. The fluid could be the fluid that is precipitated on the surface, or a sea water which percolates to the deeper region of the earth's crust, get heated up, exchanges component with the rock. So, this could be a fluid which could be a meteoric or a sea water. So, all these fluids, they are this is the totality, this the kind of fluids that we are interested in, and each of these fluids are very much characterized with their temperature and the compositional ranges. And so, we essentially try to retrieve this particular temperature and also the other parameter which is pressure, which we will be discussing later. So, temperature, pressure and composition. So, these are the three attributes that we are interested to work out of this fluid. And so, if we first take temperature, so how we go about it? So, the microthermometry means it essentially the process in which we experiment on these fluid inclusions and record the behavior or record the temperatures at which we observe phase changes. Remember that we started with this so before we do this, what we discussed about the assumptions, they remain at the basis for the microthermometric study. So, we go by the first assumption that the fluid was trapped homogeneous. So, if the fluid was trapped as a homogeneous fluid, then when we see an inclusion as this as a liquid and this as vapor, this inclusion definitely was when it was trapped, it was trapped as a homogeneous fluid. Let us say it was trapped as a homogeneous liquid. So, this homogeneous liquid, after it was trapped, when it underwent change in the pressure and temperature, there is something which happened, which we say that actually it underwent a post entrapment phase change, and in this particular case a homogeneous liquid got splitted up into a combination of liquid plus vapor. So, this our basic assumption based on the first assumption that homogeneous entrapment, that means when we see them at room temperature as a combination of liquid plus vapor, we presume that this took place after the fluid was entrapped in the cavity was sealed, and this happened as a post entrapment phase change. So, now if we recall all these combinations of the fluid that we saw through our sketches, a liquid plus vapor, a liquid plus another liquid, first one liquid 1 plus liquid 2 plus vapor, or a liquid plus solid, or liquid plus more than one solid. All these situations that we observe at room temperature, our basic assumption is that they all are a result of post entrapment phase change. So, if this process is actually a post entrapment phase change, then it is quite natural that we would like to go back to their original homogeneous position, homogeneous condition. The question is whether we are able to do that. So, if this particular thing is a result of post entrapment phase change, then our objective is to reach back to this homogeneous state and note down the temperature at which this inclusion got changed from a combination of liquid plus vapor to a liquid. So, L plus V to becoming L. So, this kind of so this is actually, it would be worthwhile to introduce the term here. So, we generally call that this is homogenization and what we do here is actually homogenization experiments. And essentially please note that we are interested in the temperature, means high temperature, means we are only talking about the high temperature situation, because this the entrapment definitely took place at temperatures well above the temperature at which we see them, beginning from anything between as we fix the range of the fluid from anything between 50 degrees Celsius to 600-700 degrees Celsius temperature. So, in respect to that, what we say that okay, what we are conducting here, we are conducting the homogenization experiment. So, we intend to bring back this particular inclusion into its homogeneous state at which it was supposed to have been entrapped. The only difference here is that this particular entrapment process took place at a pressure which is definitely higher than the pressure at which we are doing the experiment. So, we are doing the experiment at a room at an atmosphere 1 atmosphere pressure, whereas this particular homogeneous entrapment could have taken place anywhere in the earth's crust, ranging from pressure as low as 100-200 bars to going from 3, 4 or 5 kilobars or even more than that. When we go to processes such as the deeper mantle, when the diamond is forming, it could be pressure well above 30-40 kilobars or even more than that. So, that we will discuss later. So, here, so the only difference is that we are conducting the experiment at room temperature pressure, room pressure condition, that is our atmospheric pressure, whereas this particular inclusion must have been entrapped at a higher pressure. So, if we keep the pressure thing for the time being, we do not consider pressure, then if we only consider temperature, then this microthermometry is essentially intended towards obtainment or obtaining of a homogeneous state of any fluid inclusion that we are observing under the microscope, irrespective of what is the phase combination, whether it is a liquid plus vapor, or there are 2 liquids, or 2 liquid plus vapor, a liquid plus solid plus vapor, whatever may be the situation, we would have to bring them to a state of homogeneous condition, and that is we are able to achieve by heating it. By heating, and so we will see what exactly we do for that. So, microthermometry is essentially that while so the thing is that when we are conducting our heating experiment, it is very much when it is mounted onto the microscope, we are observing the fluid inclusion while we are increasing the temperature, and then able to note down the temperature precisely with a uncertainty of hardly plus minus 1 degree Celsius, that at what temperature this fluid became homogeneous, which we will be discussing now. Okay, so, for the for conducting the heating freezing experiments, we use there are devices which we call as the microscopic heating cum cooling or heating cum freezing systems. So, these are the microscopic heating cum freezing systems, and there are many such commercially available equipment where the heating freezing experiments are conducted in the temperature range of minus 196 degrees Celsius to 600, or sometimes there are different systems in which the temperature could go to 600 or go to 700 depending on the design of the equipment, and we are limited by this lower temperature is minus 196 degrees Celsius, because it corresponds to the temperature of liquid nitrogen, the boiling temperature of liquid nitrogen at the atmosphere. And there are heating freezing systems which are available, like the one which is available from Lincoln, UK. There is the stage which is available from Fluid Incorporated in a company in USA, Colorado in USA, and there used to be Kaismeka, French, and these days there are many other devices which are being manufactured by many companies with multiple applications to material science as well as geology, but our primary requirement is that we should be able to the sample or the doubly polished sample or the wafer that we have prepared, we should be able to put it inside the system which is our microscopic heating cum cooling system, and we should be able to observe them through the transmitted light, or in case of a opaque mineral through an IR light source, and would be able to observe live, so that we could record any of the temperature, any of the phase changes that are taking place at any different temperature. So, we will see some of the features of them, but it would be rather more appropriate to talk about the attributes of these kind of heating freezing systems in terms of their functionality and their usability. So, the temperature range we have already considered. So, that is minus 196 to 600 or 700 degrees Celsius. Even there are hot stages which goes up to 1500 degrees centigrade, which are specifically designed to study melt inclusions, which we are not considering in this particular course, but there are hot stages where the temperature can go to as high as 1500 degrees centigrade. The ease of operation is definitely one which is essential for us, like we should be able to easily put the sample inside the device, and we will be able to increase or decrease the temperature at our wish, the way it will be convenient for us to do the experiment, and the response time of the temperature control. So, all these whenever it comes to heating, the heating has to be done, definitely there is electric current that is needed to heat a particular object. There must be some element through which the electric current will be passed and it will get heated up, and this thing has to be controlled by specific control unit. And here as non-specialists on this kind of device, we can only talk about it that the response time of the temperature control must be very good. Means if we want to increase the temperature and we just increase the voltage, so the temperature to which the desired temperature to which we want it to increase must happen instantaneously. So, it depends on a combination of the material which is actually used for making such devices and the control unit, and so this response time of the temperature control, and the rate of change temperature in both heating and freezing. For example, if we want to observe the phase changes very carefully, and it is much more important for us that the observation should be reproducible. Giving it, suppose for example, one particular inclusion that we are observing is as a liquid plus vapor. Say for example, one inclusion which was liquid plus vapor has become a liquid by homogenization, and this takes place at 200 degrees Celsius that we observe. Now, if the rate at which we are heating the sample is too fast, then reproducing the value at 200 degrees centigrade would be very difficult. So, we need a very optimum heating and the freezing rate, so that we should be able to reproduce this particular value to plus minus 1 degree centigrade, which would be acceptable. And the provision to avoid frosting of the optical system due to cooling and overheating of the optical system during heating. So, these things are also very nicely taken care of by the devices which are available these days. When we are working in a laboratory where the temperature is room temperature of the order of between 20 to 24 degrees Celsius or so, and there we are going to, even though in a very small chamber of the device where the temperature is going down to the level of minus 100 or minus 120 or minus 196, there it is very likely that the moisture of the air will always condense on the device, and we will be able to it will affect the visibility, and the there should be a, the system must be operating in such a way that the in the lower temperature ranges of operation the visibility also should be maintained, because those are the temperature ranges where proper observation, the clarity of the observation is very important. The sensitivity of calibration to experimental changes such as heating and heating rates. Whenever we do any, as we all know that whenever we are doing any experiment and we take the reading, so the dependability or the accuracy of the temperature values that we are getting from the device is very much dependent, or it can only be obtained if we have a good calibration. So, such heating freezing systems which are used in all our laboratories, they need to be calibrated, and for that calibration we need to have some known standards. For example, we know that water, if we take pure water, the ice and water equilibrium will be corresponding to a 0 degree Celsius. If we take although we will be discussing a little later, if we take carbon dioxide, we know that carbon dioxide triple point where the solid, liquid and vapor coexist is minus 56.6 degrees Celsius, and there could be many others. So, these days when with very good quality synthetic fluid inclusions being prepared in many world class laboratories, and there the fluids of known composition are being trapped as secondary inclusions in these minerals, synthetic fluid inclusions. Those are very well used in all laboratories as standards where such kind of temperature values could be reproduced. Sometimes the higher temperature, suppose in any particular synthetic inclusion the temperature of trapping is known and the temperature of homogenization is known, those can be used as standard for our heating freezing runs when we take in our own machine. Okay, so thermal gradient is of course one situation where we are, even though irrespective of the small size of the sample, the small area in which we are conducting these heating freezing experiments, there could still be minor thermal gradient. That means when we are suppose for example we take a wafer, this is our wafer, and within that wafer there is one inclusion which is here, and this particular inclusion we are doing the homogenization experiment. So, we are definitely, so this particular this is the wafer which is kept inside the instrument, and the instrument's temperature is being sensed by some kind of thermocouple mechanism, some kind of like a platinum resistor or some kind of chromel-aluminum thermocouple, and is depending on the voltage and current, it is calibrated with the temperature and it is indicating a temperature, let us say any value, let us say temperature T1. Now, the thing is that whether in this entire sample the temperature could be T1, and we are more interested in exactly knowing the temperature, it is exactly it is what here. So, it may be just about few millimeters away, that this side and that side, or so here within that there should not be any thermal gradient, so that the temperature that is recorded here and is being sensed as a whole for this particular area by the device, there should not be any discrepancy. And the ease of access for sample changing and calibration means whenever we are changing the sample holder, this thing should be very well designed, so that there will be a good ease of operation. The ease of changing of the objectives during a run, this is not that very important, but sometimes it is required that during our heating freezing experiments we are relocating the inclusion, the inclusion that we took a freezing run sometime and we want to get it back and take a heating run, we may have to change the objective to a smaller magnification, and then so this kind of change of objective while the microscope stage is actually fitted with the hot and cold system. So, this also is an important criteria for the hot and cold system that we will be using, and the ease of changing between the heating and cooling modes. For example, even though we have not considered the low temperature part, we are talking about temperature only, but as we know that we need to do a freezing experiment on these inclusions also for knowing their composition, and then we want to change the mode from the inclusion that we froze. We won't immediately want to take a homogenization experiment or homogenization run on the particular inclusion. This kind of switching up between the heating and the freezing modes should be very easy for us. And the size and the thickness of the sample to be accommodated is another criteria that should come in evaluating how good or how bad or how effective or how good a device could be for our purpose. And the diameter of the field of view and the permissible movement of the sample, because generally it would be good to have a bit of an idea that what kind of dimension that we could be using. When we take a sample and we prepare a section, this sample, let us say it could be something like a 35 mm to 25 mm, that means 3.5 centimeter to 2.5 centimeter, and on which we have mounted a section of our sample that we wanted to do the fluid inclusion study, and this will be of the order of, say, for example, 2 centimeter by 3 centimeter or 1.5 centimeter by 3 centimeter kind of a size, and this is the doubly polished thin section or the wafer that was prepared to study the fluid inclusion. So, this wafer, which is mounted on a slide by using some adhesive like a Canada balsam, is basically be taken out and will be put into the hot and cold stage. But the stage, the sample holder or the area could possibly be just about a 1 centimeter or at the most 1.5 centimeter diameter circular sample holder on which the sample could be put. And then even if this sample is put inside the sample holder like this is possible. Suppose this is the sample which is put inside the sample holder and has to be again smaller in its dimension. So, that means the wafer which was prepared of a particular dimension has to be broken into smaller pieces or chips and will be loaded onto the sample holder of the device. And now, once it is loaded into the sample holder, the device also should allow a sufficient amount of the movement in the x and the y direction, so that as much of area of this particular wafer should be visible to us. So, we will come back to the discussion of on this particular aspect as to what should be the size, minimum size or the maximum size of this wafer which will be loaded into a sample holder of a hot and cold system. This also is very important when we plan our microthermometric experiments, which we will be coming back to this particular point again later. And then the situation is that these devices, they work on liquid nitrogen, or till so far we have been able to use liquid nitrogen. We have not been able to use any other gas which would give us lower temperature than that. So, that is how we are limited to a temperature range of minus 196 degrees Celsius. So, we need to have constant supply of this liquid nitrogen and other kind of maintenance of the equipment that is necessary for keep it in a running condition. These are the for example, the consumptions of the consumable part. We might just look a little bit details into one particular type of hot and cold stage and what kind of consumables or the accessories, peripherals that we use there, or you may get it from there from standard literature as well. and then the peripherals like the quality of temperature control at any temperature, which actually we were so that means the design of the control device is such that the quality of the temperature control should be to the best possible for us, and the readout capability versus visual record. In today's situation, most of the equipment are computer controlled, and the microscope is attached with CCTV, and the images are very well displayed on computer monitors with good graphics card, and we can get a very good image, the very good visual effect of this particular inclusions which we are studying and taking microthermometric measurements while observing them under the microscope. So, visual recording is almost like there was a time when the phase changes used to be recorded through the eyepiece, and then the temperature at which it to be recorded has to be manually recorded. Now, this particular situation has improved a great deal, and the readout capabilities like the display device of that particular heating freezing system, that means the temperature at which a particular phase change has occurred has to be recorded effectively, and sometimes also can be put into the memory, and so that the data can be utilized. So, this was also one of the things which is important, and there has been significant improvements on this particular area over the last 1 decade, where there is now very remotely operated or touchpad type systems, where the hot and cold stage could be operated for decreasing or increasing the temperature, the rate at which the temperature should change. Sometimes we can even go up to as low as these kind of hot and cold stages. They operate in a situation where the temperature rate of change could be as low as about 2 degrees centigrade per minute to even as high as 25 degrees centigrade per minute. And if we are taking the doing the microthermometric experiment on any inclusions and would like to go to temperature, and then this particular gradient or this temperature, the heating or the cooling rate also could be very variable. For example, if a particular inclusion which was a liquid plus vapor at room temperature, and a homogenization experiment is taking place, is being conducted, and suppose this particular liquid plus this inclusion homogenizes to liquid and a temperature of 250 degrees Celsius. So, we were interested in a precise recording of 250 degrees Celsius, not actually much concerned about how many times we can change the heating rate to make a compromise between the time taken to have such microthermometric experiment done on because it can be very well visualized that we have to do microthermometric experiments in each and every individual inclusion and in hundreds in numbers. Sometimes it actually depends on what is the dimension or what is the area on which the work is taken up and what exact problem we are actually addressing. So, their number of inclusions that is required to be studied for microthermometry or microanalysis is quite variable. So, when I have to measure the temperature, record the temperature in 250 degrees Celsius, going from room temperature of 25 degrees Celsius to almost like 200 degrees Celsius, this could be done at a much faster rate, even going up to 20 degrees centigrade per minute or even more than that. But as the temperature of homogenization would be approaching, for a proper reproducibility and the recording of the temperature without introducing any error, there the rate of heating should be as low as possible. In the heating cycle, the rate could be a little higher, but in the freezing cycle the rate could be the minimum possible, which we will be discussing. So, there should be a this remotely actuated recording, the short term precision, the reproducibility and the long term precision of the results, that is the drift. So, this, as we discussed, is coming from the periodic calibration of the equipment, where there is, so that there is no long term drift of the equipment. If any hot heating freezing system has to be periodically calibrated. For example, if I calibrate it today, I may need to calibrate it just about a month later or even a week later, depending on how the equipment is actually behaving. And sometimes many of the situations that we observe, that it does not actually shift much, but it is a routine procedure to check or to recalibrate the instrument with the standards, and so that the drift could be taken care of. And the pressure, since it operates on liquid nitrogen, which is volatile and it is actually gas at the room temperature. So, you need to have a proper circulation system. So, that is inbuilt into the system how the liquid nitrogen will be circulated. In the systems like the Lincoln stage, the liquid nitrogen circulation is done by a liquid nitrogen pump, which can pump the liquid at any controlled rate manually or could be automatically set. And the another important aspect of the hot and cold system is the volume of liquid nitrogen that would be required. In systems like the fluid incorporated adapted the fluid incorporated hot and cold system, heating cum freezing system, there the volume of liquid nitrogen required is more, and in case of a Lincoln stage the volume of liquid nitrogen required is less, because in a fluid incorporated hot and cold microscopic heating freezing system, there is no liquid nitrogen pump. It actually just is circulated by using dry nitrogen gas, so that it carries the cold nitrogen gas through the sample and can cools it. And sometimes the as in case of the fluid incorporated adapted stage, hot and cold stage, the heating is done through a heating coil and by passing compressed air through the heating coil, but this problem the system the heating system in Lincoln stage does not require any compressed air. So, these are some of the considerations or some of the characteristics, attributes of the microscopic heating cum freezing systems that are utilized for conducting microthermometric experiments on fluid inclusions. So, we conclude our discussion today, and we will continue with the principles of microthermometry in relation to the entrapment of various types of fluid inclusions with correspondence to their phase behavior in high temperature as well as the low temperature regions. So, we will continue the next class. Thank you.